Hi everyone, I'm Tal, and in this video we are going to learn about automatic hyperparameter tuning with Optuna and PyTorch. So let's begin. Okay, so hyperparameter tuning, we have discussed that it's important. It can be a very cumbersome process, and sometimes we are going to have a lot of hyperparameters and we can be clueless of the search space. So there are a couple of techniques to tune the hyperparameters. The first one is babysitting. It's also trial and error, 100% manual, and most widely adopted by all of us, right? And the problem is that sometimes it's not very scientific, and of course we can miss the optimal search space, and it can take a lot of time, and it very much depends on our patience, right? And the second option is grid search, so basically systematically going over all of the possible combinations for our hyperparameters. Now, the problem with that is that it can take a lot of time, but of course it can be parallelized, and we can, if we must report the values of each hyperparameter, then we must use, we can avoid grid search, right? And it does not consider history. So if there was a bad combination, or a direction of bad combinations of hyperparameters, we are still going to go that path. Nothing stopping random search for running these trials. And of course, if we have a lot of hyperparameters, then it can take a lot of time. The second approach is random search, and the idea is very similar, but instead of going systematically over all the possible hyperparameters, we just randomly sample them. And you can see that so it's empirically validated that for a given time, then if you run random search and grid search, then random search will yield the probably the best combination of hyperparameters that will lead to better performance. Okay, so in deep learning, if you still want to use you still want to use like some of these techniques, then random search is better than grid search. Right, now the last option is Bayesian optimization, and the idea is that we can actually, as we try out different combination of hyperparameters, we can actually go to the side and build a model that predicts the accuracy or the whatever objective that you try to optimize given the hyperparameters. So basically this helps us focus on more promising areas, and basically we can discard trials that are not promising because we know that we have already searched in these areas and there's nothing good in these areas. And the idea is that we are going to initialize the searching process with random search probably. Then we start running trials, and we update, as we go along, we update our model, which predicts the probability of a successful trial given the hyperparameters. Now, it's usually much better than random search and of course grid search for a given amount of time. And it might be a bit more difficult to implement, but we have a framework for this, so you don't have to work that hard in order to use Bayesian optimization. So this table here summarizes all the techniques that we have. So babysitting and grid search are not recommended for deep learning, and random search and Bayesian approaches work well for deep learning. And basically, we are going to talk about today about Bayesian optimization today, and you'll see that it's not that hard to use, and it's very recommended if you have a model that you are not sure about its hyperparameters. So Optuna is an open source hyperparameter optimization framework to automate the hyperparameter search. It allows easy parallelization and quick visualization of the hyperparameter space. So if you have multiple CPUs and GPUs, then you can utilize them and basically parallelize everything. So it can also be much faster. Now it can easily be installed with Anaconda or Pip, and according to your favorite environment management tool. Okay. So Optuna basically uses two strategies, so sampling strategy and pruning strategy. So sampling strategy is which areas of the hyperparameters to sample from or where to look, and this is this model that we are trying to build on the side, so the probability of the accuracy given the hyperparameters. And we also have the pruning strategy, so if a particular trial is not looking very promising, even though the combinations of this trial were chosen according to the model that we are trying to build, so the sampling strategy, then we should decide whether we stop this trial or not stop it. So it can actually terminate an unpromising trial at early stages and save time. Right. So let's start with samplers. So where to look. So the idea of Optuna is to focus on areas of interest using Bayesian fitting to find a place that it has had the best results and continue to look in that direction. Now, in the figure below, you can see that random search, it doesn't care about the history, it doesn't build any kind of model, so it just samples combinations. So basically, we might cover a larger area of the search space, but we don't actually focus on promising areas, so where the minima is. Right? Now, Optuna, on the other hand, but using Bayesian fitting, then we can actually focus on more promising areas. So you can see that there are more trials, so the blue dots, in around the minima. Right. So we have a couple of types of samplers. So how we can navigate to more promising search areas. The first one is called tree structured Partisan estimator, TPE. This is the default one, and basically it's based on kernel fitting. And when you initialize Optuna, this will be the default sampling strategy. Now, we can also actually change that. So we have also Gaussian processes, and we also have CMAES, which is a meta-heuristic algorithm for continuous space. And if you still want to use random search and grid search, you can use them with Optuna. It's simpler than implementing them by hand. So there is an official cheat sheet by Optuna. So how to choose a sampling strategy. So how many trials you have. So if you have more than 1,000, then maybe CMAES is better. If you have less than 1,000, there is some rule to choose between the TPE and Gaussian processes. But a good default is TPE, and this is what we are also going to do in this tutorial. But you can change it and see what is the outcome. Now, what about pruning? So there are two strategies, so median pruning and successive halving. And successive halving works usually in practice. We are not going to talk about it anymore. Just know that the idea is to choose the correct time step to prune a trial when it's unpromising. So as we know in deep learning, sometimes we can start bad, but then get to good areas. So for example, you can take a look at the brown one. So we can see that the brown one is actually starts bad, but then actually reaches like the pink one. And maybe we should not have pruned it earlier. So this is what the pruning strategy decides. But successive halving is usually a good strategy. So it's also the default one. So we'll stick with it. So let's do this example and see how we can use Optuna. It's quite simple. We just need to become familiar with the terms Optuna uses. So the first one is study. So this is the experiment. So for example, in this tutorial, we're going to find the hyperparameters for a fully connected network to classify MNIST. Trial, as the name suggests, it's just one run of the model with the chosen combination of hyperparameters. And direction, so very similar to if you recall from when we talked about schedulers. So reduced learning rate on plateau, we need to define the direction of the objective so we can minimize or maximize. So if you check accuracy, then we want to maximize it, and if we look at the error, or for example the reconstruction error, then we want it as low as possible. So we want to minimize it. So a template code looks like this. So we have an objective function that accepts a trial, and we write the code, then we return the evaluation score. So at the end of this part, we'll probably have some validation loop. Then we have study, we create study, we give it a name, give it the direction, choose the sampler, and then start to optimize. And you need to define the maximum number of trials. So you don't want it to run forever, we want it to stop at some point. right? And what you optimize is the objective. Okay, so the objective is going to have all of our model definition and all the hyperparameter, how to pick the hyperparameters, and we'll see an example right now. So first of all, we have some definitions. So in this case, we pick constant batch size and number of epochs, but this can be optimized as well. We pick the device like we always do, right? Now, here's the thing. So when you tune the IP parameters, sometimes you can just, you don't need to run a full experiment. So you don't need to run it for 200 epochs. You can just use 10. And you don't have to use the entire dataset. You can just use a portion of it. So we do this just to get an idea where the wind blows. So we'll use Optuna on a smaller dataset for a shorter training time to get a feeling what are good combinations of hyperparameter. And after Optuna gives us the output, we will take it to babysitting and we'll try to manually find the correct combinations by running full experiments. You can also do this with Optuna, but for this case, we just use a subset to get an idea of what good hyperparameters look like. So we have a function to get the dataset, which gives us data loaders for the training and validation. Now, the next thing we do is we define our model, and the model is defined by hyperparameters, right? So we need to use Optuna to give us suggestions of the hyperparameters. So the way we do this is we call the trial.suggest float suggest in, depending on the type of hyperparameter. We can also have suggest categorical, so we'll see that in a minute. Now, for each hyperparameter, we need to specify a range of possible values for Optuna to choose from, right? And of course, for clarity, we also need to give an informative name for each hyperparameter. So our defined model accepts the trial instance, right? So, and now we actually use Optuna to give us suggestions for the hyperparameter. So number of layers. So we ask Optuna to give us a suggestion for an int value. So we can pick between 1 to 3. So it can also be 2, right? Now, when you call trial.suggestInt, Optuna actually uses the learned model for the hyperparameters. So it's gonna choose this hyperparameter based on the model that it tried to optimize. Now, now that we have the number of layers, so Optuna gives you a picking of the hyperparameter. Now we are going to optimize the number of units. So again, we can use Optuna to suggest the layer size, right? The number of hidden units, right? And the number will be between 4 and 128. Cool. In this case, we do not optimize the activation, but we can also optimize the activation. We also add dropout. In this case, we suggest float because we know that dropout is a float number between 0 and 1. So in this case, we optimize between 0.2 and 0.5. Now it's just for an example. Basically, dropout can go to 0.5 and 0.1. So maybe this range should be a bit to the left, right? And then we have the rest of the network, which is the output, which is the number of classes and the softmax. Okay. Now we actually get to the part where we define the objective, and this is the function that will be given to Optuna. So the first thing we do is we create an instance of our model, and we use this using the function we created above. Now note that the objective accepts the trial, so don't worry about it. Optuna will take care to propagate the trial instance for all the sub functions. So trial is from Optuna. Don't worry about it. It will be given to this to the model. So we have access to Optuna all the way. Now we have other hyperparameters. So for example, the learning rate. So we suggest float here. So we choose between 1e-5 and 1e-1, and you can tell Optuna to go at a log scale, right? So just a log scale value. So 1e-5, 1e-4, and things like that. We also want to choose the type of optimizer, right? So in this case, we suggest categorical. And there are two ways to do this. In this case, we just have the name and then we use the get attribute function. And then we initialize the optimizer. Then we have the initialization of the dataset, and of course the standard loop, right? Now here we break the loop if we exceed the number of maximum samples, just so to save some time. And we do this, we train the model as usual, okay? Nothing here is new, okay? And at the end of each training loop, we have the validation loop, right? And we just use it, just calculate the accuracy on the validation, and we report to Optuna what is the accuracy. Now this is critical because this is how it's going to update its internal model of its internal Bayesian model, right? Now finally we add this trial.should_prune. So in this case, in this part of the code, we tell Optuna to use its pruning strategy to decide whether to stop or to continue this trial. So, and this is all happens inside the epoch loop. And in this case, we only run for 10 epochs. So it's a very small number of epochs, and it can help us decide if the combination of hyperparameter is good or not. Now, once we define the objective, which utilizes both the defined model function and also the get data function, we can actually start the process. So first of all, we choose the sampler. In this case, we choose TPE. It's also the default one. You can change to Gaussian process or CMA. Then we initialize our study. So Optuna.create study, you give it a name, hopefully an informative name. You tell it that when you report the values, so here you report the accuracy, so you want to maximize it. If you had reported the error values, then you wanted to you would change it to minimize it, and we give it a sampler. Now you start the optimization process. So study.optimize, and you give it the objective function that you defined above, the maximum number of trials, and you can also have a timeout. So sometimes it won't reach the number of trials, but if you give it a very limited time, then it will stop before it. Okay, so if you only have a budget of training hyperparameter tuning for 1 day, then it's okay if it does not reach the number of trials, but just stops before that. After we are done, then we can actually print all the statistics. So we can print the number of prune trials, the number of completed trials, and we also have access to the best trial and the value and all the parameters, all the hyperparameters that it is chosen. So you can see the output of Optuna here. So we start with trial number 0, and we initialize Optuna with a random search. So not surprisingly, the accuracy is low, right? So 9%. But as we progress in the training, then the model will be updated, and we will focus on more promising areas. So we can see that trial number 5 and 6 were pruned because they are unpromising, but when we reach trial number 7, we already reach 88% accuracy. And a lot of trials are going to be pruned, so a lot of time is going to be saved, right? And you can see that by trial number 20 or 30, we are already at 94% accuracy, and it runs and ends. And then we print the statistics. So we told it to run 100 trials. More than 50% of the trials were pruned. So this is good. So a lot of time was saved. The best trial yielded a performance of 95% accuracy, and you can also print and see the chosen hyperparameters. Now, the next step would be taking these values and now trying to play around them with the full experiment. So on the entire data set, right? And also for more epochs, so for more time. And then here you can take it to babysitting, or even using Optuna and just changing the range of the hyperparameters according to this, and run longer trainings. Now, Optuna also provides us with nice visualizations. So, for example, we can see which hyperparameter was more important to give us the best performance. So we can see that the number of units and the learning rate were most affected the accuracy the most. So this means that when you are going to take these hyperparameters and manually tune them, then what you should look at is probably the number of units and the learning rate. Another thing we can get from Optuna is a visualization of the search space, and we can see a plot where it focuses most of its trials. So we can see that it focuses on areas which are more promising. So as we go brighter with the color, then the performance is better. Right? And of course, and we can do this for every combination of hyperparameters. So we did it here for the dropout and the number of units, but we can also do this for the number of layers and the learning rate, right? So very dynamic, and this is it. So a very nice tool. You can do this with any kind of network, and of course, not only for PyTorch, you can also use Scikit-learn, and of course everything will be faster because classic algorithms run faster than neural networks. Okay, that's about it. If you want a deeper dive into Optuna, there's a nice video here, and that's it. So thank you for watching.